um, when we were at Smith Falls and we were testing out the probe, the active probe, Peter was doing some sweeps with the spectrum analyzer, and we were getting some results, and we kind of scratching our heads. So we thought, hey, let's use a scalar network analyzer. That's the PARC SNA we built back in 2018. And we dusted it off, got it working, and it gave very similar results. And I was pretty impressed that it worked that well. So, Peter and I got talking, and we thought, well, maybe we should dust this thing off and talk about it a little bit more. So I said, I did this presentation back after we had built the SNA, and it was basically a presentation about how the SNA works. It's not meant to be a how-to video, how to use it, but it's basically explaining what the various pieces are doing. And just as a cautionary note, with all my presentation, I may not know what the hell I'm talking about. So take everything I say with a grain of salt. So what this is it's a how it works. So here's the PARC SNA completed with glass case, which I'm impressed. We did a really good job with this. Frank, hats off. We did a fantastic job putting this together. It was a good teamwork, and we pulled it off, and it was a good piece of equipment. And so the PARC SNA, for those who don't have it or haven't used it, it generates a bunch of charts. And I'll go through what some of the charts are. The nice feature is that it can do overlays, where we could put multiple charts on one screen. It'll do 3 dB. It'll actually give you the 3 dB points of a filter, and you can see it here. I don't know if you can see start, stop, 3 dB 1, 3 dB 2. And here it's giving you the crystal motional parameters of a crystal. And so it's pretty useful, I think. So what this is not a user guide. I'm not gonna go through, how to program the Arduino Mega and the TFT display and how I2C works and how a thermonuclear bomb works. I'm not going through that. There is I did a bunch of YouTube videos. If this finally comes up here, it's taking its sweet time. So here it is here. So there is a playlist I've got. It's got a whole bunch of videos about how to. This is the how to. It shows you how to do filter sweep, how to use the return loss bridge to do SWR, how to calibrate the device, how to calculate the crystal motional parameters, how to use the amplifier, how to sweep an amplifier. And it's got a unique feature where you could do almost everything from a CLI. And these two presentations, these two videos here explain how to use it and how to export data and et cetera, et cetera. So if you're looking how to use it, that's the place to go do it. Myself and Peter wrote the manuals for this. I can't remember. I think I did a bit of it, and then Peter did a bit of it, or Peter did most of it. But there are a set of comprehensive manuals we've got about the device, so that's where you should go if you want to learn how to use it. So from a high level, a conceptual design, this is basically how the SNA works. So we've got a signal generator. It generates a signal, and that signal, we know what the amplitude is, and I'm going to talk about that in a second. But we basically know what the amplitude and frequency of that signal going into a device under test is, DUT, device under test. And then we've got a signal coming out, and we've got a detector here that detects the signal coming out. And so based on that, we could sweep along a set of frequencies and plot what we see coming out. And from that, we can, look at filters and figure out SWR and all that good stuff. So that's conceptually how it works. So now I'm just going to talk about some of the use cases you could use it for. So first one, it's, as I said just now, you could use it for doing kind of a frequency dependent analysis. You look at how the output signal from your device under test, you're looking at this output signal here, how that behaves as a function of frequency. So some examples of how you could use this is a cable. You've got a 50 ohm cable, and is the cable good? Is it bad? Well, you could send a frequency down it, and you could see how it behaves at frequencies to see if maybe it doesn't work very well at in the high bands and the high HF bands, or maybe it works better in the low HF bands. An amplifier. You could put an amplifier on this, and you could see, how it works, how it sweeps across the frequency. Low pass filter, is your antenna tuned properly, etc. So you could do a non-frequency dependent analysis because it does have a power detector, and that allows you to measure how strong the signal is. So you could feed in a VFO, a PLL signal, and you could see how strong that signal is coming out of a device. You can see how strong a signal is coming out of an amplifier. But you got to be careful. Here, danger, Will Robinson, is that you got to be careful with amplifiers because an amplifier could blow. It could have too much power for the detector, and you could blow it. And I said here, you could use this for SNR. I don't think you can, because after looking at the active probe and trying to figure out the signal to noise ratio, the noise floor for the active probe, I don't think you could do this, but it may be possible. Maybe someone smarter than me can figure it out. You also have a frequency generator. So you basically have a SIGGEN as part of this, and it's got a signal source that you could experiment with. It's a quick and dirty oscillator. You could use it to fix a mixer, to modulate it, to test a mixer, to do all kinds of different things. So let's now talk about the components. So let's talk about the generator part of it. So the frequency generator is based on the 809851 DDS, and that was a module that we could get from China back in the mid 2015s-ish. That was very popular as an oscillator, and the nice thing about it, it was putting out a sine wave, and it uses a 30 megahertz crystal with a multiplier, and it's basically advertised to go from 0 to 70 megahertz. But we found, somewhere around 30-ish megahertz, you start seeing harmonics, and the sine wave becomes less of a sine wave. So it's less clean. So the issues with this is that, number one, it's not 50 ohms output. And even worse, the impedance varies with frequency. So it's not a flat impedance right across the board. Even worse, the signal amplitude varies with frequency, not a lot, but it varies, by a few to several dB. And the signal quality deteriorates above 30-ish megahertz. So you get some harmonics coming out. And so the 9851 is connected to a microcontroller. In this case, we were using a Arduino Mega, and that selects what frequency that's coming out, that's being generated. So the way we attempted to fix some of these issues was that, the microcontroller turns the DDS on. Then the output from that goes into a 20 dB pad, and it's a 50 ohm pad. And then it goes through a 60 megahertz low pass filter just to clean up some of those harmonics we'd see, around the 30 megahertz output frequency, so that will kind of clean up some of those nasties coming out. Then we added back a 20 dB LNA at the back, and I think, Peter, we used a MAR 6SM for that at the back end. So, we have a 20 dB loss here, 20 dB gain. Net effect should be the same, ignoring any insertion loss from the filter here. And, we got a fairly steady RF signal coming out. So now let's talk about the detector side of it. This is based on the 8307 chip, which many of you would remember from Wes Hayward. He published that article way back when, how to make a power meter using a 8307, and he had it connected to a meter. And there's been a lot of iterations of this over the years. But basically, it's a very sensitive logarithmic amplifier. It measures, output signals down to, it's advertised, down to about a -70, -80 dBm. And keep in mind, a strong RF signal is S9, which is -73 dBm. So this is putting out a fairly strong RF signal that your antenna would receive. So it puts out a DC voltage proportional to the power of the signal. So whatever signal it's got coming in, it's going to put out a DC signal, a DC voltage that the microcontroller is going to use its ADC to detect the voltage, and then that's going to tell it what the signal is. Now, it's very sensitive to noise. So you've got the power supply could generate some noise, and that'll impact the 8307. The RF signal itself could have noise that's coming in. The microcontroller has a clock, and it's switching on and off and flipping bits, and that's generating noise on the PCB itself. And you've got the generator, which is also generating, it's an oscillator, so it's generating noise. So we have to figure out a way how to tame some of the noise here. So this is kind of what we did. Now, this splitting up the regulator because the 8307 needs 5 volts to run, and I think this splitting this up was something that Kelly did, and I think he did it more for heat dissipation, because to go from 13 volts to 5 volts, that poor 5-volt regulator is going to be dissipating a lot of heat. So by doing this, you've got 2 steps, and you dissipate less heat. So the 8-volt regulator is feeding, a 8-volt voltage to the microcontroller, and then the 5-volt regulator is feeding the 8307, and that is going through a LRC low-pass filter. So that's an inductor, resistor, and capacitor. So that's trying to tame any kind of noise that's coming in along the line that's going to the 8307 as well. The DC output from the 8307 is going through an RC low-pass filter to try and tame that. As well, we're doing some crude DSP processing in the microcontroller to try and tame some of that noise. And we also have a isolated ground plane that the 8307 is sitting on top. And this ground plane and the ground plane for the larger PCB is connected via one single 0-ohm resistor to try and minimize, multiple paths and ground loops and all that kind of stuff. So far, what we have is we've got a microcontroller configures the generator. It generates an output signal. It goes through the device under test. It comes out, the detector detects that, and it produces a DC voltage. So the problem here is that we have no idea what the output of this generator is. We don't know if it's 0 dBm, -3 dBm, +5 dBm. And I said that the output varies with frequency. So we have to figure out how we're going to know what's coming out of here. And I'll talk about that in a subsequent slide about calibration. And similarly here, we've got a DC voltage coming in. How the heck is this microcontroller going to know that 3 volts equates to, say, 0 dBm? So that's where we have to do some calibration. So I threw this slide in here just to talk about the return loss bridge. It's a device under test. It's a DUT here. The return loss bridge is connected here, and it has a signal coming in. It's got a signal coming out, and it's connected to an antenna. And the return loss bridge is used to generate return loss, SWR, and impedance. And the impedance is very low. It's 50 ohms plus or minus, say, 50 ohms. It's certainly not going to detect a 200 ohm or a 500 or a 1K ohm load. It's going to be something very close to 50 ohms. The way the return loss bridge works, I think you guys all know this. You've got a generator feeding in a signal to the return loss bridge. If no antenna is connected, the output port, all of what's going in comes back. You have a large reflection coming back. And in that case, you've got a low return loss. So the return, there's no loss. What's going in is coming back. So you've got a low return loss, and you've got a high insertion loss. So what's going through, you've got a lot of loss going through. So you've got a lot of insertion loss. And conversely, if you've got an antenna connected, it's perfectly matched, then what goes in comes out here. Everything is going into the antenna, and very little signals being reflected. And in that case, you've got a high return loss. Everything that's being returned is being lost. And you've got a low insertion loss because everything is almost going through. There's no losses going through. Almost no losses. So the way I visualize this is using a dartboard. And so if there's no antenna connected, the target is really small. So if you look at these targets here, let's just say that's what you're shooting at the dartboard, you're going to miss the circle. You're going to be outside the circle, and everything is going to bounce off. Whereas if it's perfectly matched, you have a really large circle, and anything you throw at the dartboard's making it through. This is something similar to something in nuclear physics called the nuclear cross-section. And you see that with certain particles have to have a certain speed, certain energy in order for it to interact with another particle. So that's kind of why I kind of visualize it this way. So putting this all together now, so we've got the programmable microcontroller, the Arduino Mega. It's connected to a display. It's got some memory, and this, you basically go on the front panel and you tell it sweep this frequency to this frequency, and blah blah blah. And so it goes out here and it generates a signal, puts it through the device under test. It comes out here, detector detects it, then it plots it on the screen. So that's basically how it works. And there's also a feature in it. It's got a CLI, command line interface, where anything you could do with the front panel, you could do with the CLI plus more. Plus, you could also export the data to a connected PC for, like, if you want to put it into Excel. Okay, so I talked about some of the issues with how do we figure out, what 0 dBm is based on that voltage, and the signal coming out of the 9851. So let's talk about calibration now. So the first calibration is the 8307. So we need to calibrate that. So we need to be able to know what that DC voltage coming out is, how that equates to a dBm. So that's the first calibration we need to do. The next calibration is the 9851. That crystal is not perfect. because I said that it has a onboard 30 megahertz crystal. It's got a 6 times multiplier, then it divides it down and blah, blah, blah. But that 30 megahertz crystal could be 29.9998 megahertz, or some other frequency, and that could cause the output frequency to be different. So we need to correct that. So we need to know that if I tell this I'm putting out 10 megahertz, I'm putting out 10 megahertz. The next thing is that we need to know the signal strength of the 9851. And so we need to be able to calibrate that to know that if I put out a 5 megahertz signal, I know the signal coming out of the 9851 is going to be minus 10 dBm, or whatever. I need to know exactly what it is, because then what's coming out of my device under test, I could make a comparison. So the way we calibrate the 8307 is fairly simple. We have a signal generator here. I use the XG3, which is not, it's a terrible way to calibrate this, because the XG3 is not an accurate source. It's a good ballpark, but it's not an accurate source. You should use something that's got a fairly good, signal strength and frequency, and clean. And I think at the build-a-thon, we used some of Simon's equipment. He brought along some of his frequency standards, and we calibrated the SNA using his equipment. So this is very straightforward. So basically, when you go to calibrate the 8307, it asks you to enter 2 dBm levels you're going to be putting in, and it measures the voltage and it stores it in memory. Remember I said back here it's got memory, so it stores that in the memory, and what it does, it calculates slope, intercept, and it's able to figure that out. I'm not going to go through the math, but just know that after you do this, it can figure out what the dBm coming out of that 8307 is. To calibrate the 9851, the frequency accuracy, we need a signal, we need a counter, a fairly accurate counter that's able to measure the frequency that's coming out of the 9851. And so what we would do when we go to calibrate this, we select a frequency, say 10 megahertz, and we look at the frequency coming out here, and if this is 10.0001 megahertz, there's a knob we turn, and we adjust the compensation factor until this gets as close as possible to say 10 megahertz, or whatever frequency we set. And that compensation factor, it takes that and it stores that in memory, and it uses that from that point on to ensure that the frequency coming out is what you need it to say. So now the next thing is, how do we know what the amplitude, how strong that signal is coming out of the generator? Because I said that varies with frequency. So we do exactly the same thing we do with our spectrum analyzers. With the tracking generator, we connect the cable from the generator to the detector, from the tracking generator to the SA, and we do a sweep, and we normalize that. We know that, okay, this is what our tracking generator is putting out. And when we put a device under test, we could see how it performs relative to that. So same idea here. So basically what this is doing, when you go into the calibration of the output of the AD9851, it generates frequencies from 1 to 33 megahertz. And it goes, I think here it's going up in, what's that, 70 kilohertz steps. So it's going up, and it's measuring, it's putting out, say, 1 megahertz. It measures the signal voltage. Then it goes up to 1070 and so forth, and it goes all the way up to from 1 megahertz to 33 megahertz. I'm only showing here a small section. And based on that signal voltage from the prior calibration, it knows that 2 volts is, say, minus 9 dBm, and 2.01 is or 2.08 is 9.1, blah blah blah. It knows what that is. So, and it takes this table and it stores it in memory. So when we do a sweep and it wants to know what's coming out of here, it goes to this table and says, oh, okay, at 1210 kilohertz, the output is minus 9.1 dBm. So that's what I know what's going out. Look at what's coming out from the device under test. Okay, so this is a really important point, and this could really mess you up here. Is that, okay, the LCD I'm using, it's a TFT display. It's basically 480 dots across by 320 dots across. And I divided the display up into 4 areas. So at the top, there's a small banner, there's a plot area, and here is where you see all the data, and you start and stop frequencies and all that stuff, and then a banner at the bottom. So the plot area comes out to be 478 dots across by 220 vertical dots across. This 478 is important because when I do a sweep, I'm doing 478 measurements, period. I don't do 1,000 measurements. I don't do 200 measurements. I do 478 measurements always. So 1 dot represents 1 probe. And I do that for simplicity, for plotting, to make it faster and easier. The issue with doing this is your resolution. Okay, so for example here, let's look at a case where I'm going from 1 to 2 megahertz, or I'm going from, this could be 3 to 4 megahertz, or 5 to 6 megahertz, doesn't matter. It's got a 1 megahertz span between the start and stop. So because I'm doing 478 points, the resolution is 292 hertz, for example, for the 1 megahertz sweep. So what it means is that I make a measurement at 1 megahertz, then I set the programmable, the controller sets a generator to go up by 292, 2.092 kilohertz, right? Goes up, then it makes a measurement, and it stores this in memory, and it does this 478 times. And you can see it here. Each time it's going up by 2092, which is the resolution. Okay, so it does this, and then it takes this and it plots it. That's what it plots. That's it. Bingo, right? The reason I'm bringing this up is this 478. If you do a sweep from 1 to 30 megahertz, that's a 30 megahertz span. So you take 30 megahertz, you divide it by 478 measurements, your resolution becomes really large. Well, large or small. The increment between your measurements is huge. So you're going to lose, you could lose some information. So this is very, very important. So you got to choose your start and stop frequency appropriate for what you're measuring. Otherwise, this could lead you down the garden path. Okay, so that's basically the presentation. So I just got a couple of closing thoughts, a couple of things here, some things which will bite you in the ass, 100%. So first thing, it's how low can you go? Okay, the 8307, as I said, advertised you could go down to minus 80 dBm. I haven't seen an 8307 go down below, say, minus 55 dBm, just because of the noise, because that noise floor. And I said, you know, you got RF noise, you got, you know, noise on the from traces, you've got all kinds of parasitic noise, and that may cause the noise floor to go up. Now, this is very, very, very important. The 8307 is scalar. It's like it's open. It's very wide bandwidth. It's going from DC to over 1 gigahertz. So anything in that swath, anything that's coming in, it's going to take it and it's going to add it to the power. So in this case here, just say that's the signal we want to measure, and there's some harmonics or some junk. The 8307 is going to take the power here and add it to the power here and add it to the power here. And I think it does like a root mean square or something like that. It's not a linear where you take this, add it to that, add it to that. But it does mess it up. So That's why the 8307, we tried to clean it up as much as possible. Remember way back here, you know, where was the, where's the diagram? Here, we put this low pass filter in because we're trying to restrict how much, you know, junk we would get coming out beyond the 60 megahertz, because we found, you know, around the 25, you know, 30-ish megahertz, we started seeing harmonics coming out. Okay, so that's a gotcha right there. The next gotcha is calibration of the 8307. So because we're using a 2-point calibration, we could get some errors in the slope and intercept. So here I'm showing 3 different calibrations where the calibration values that we used, the 2 points we used, differed slightly a bit. And you could see it down around, what's this? This is around 3.5 volts. I think that's voltage here. So around there, it's pretty much the same. But as the voltage goes up, right, you see a bigger span here, and you see a more error. So, and in this example, at about 10 dBm, the error is about 3 dB. And that shouldn't be dBm; it should be dB. And at 70 dBm, minus 70 dBm, we're getting, you know, a 5 dBm difference out towards here. So it's huge. So, you know, you have to try and get your calibration of your 8307 as accurate as possible, because otherwise your data could be off a bit. The other thing is scaling. Now, here's 2 different scalings. This is showing a scale here of 0.1 to 9.1 SWR, showing the same sweep. And we can see the 2 dips here, seeing a dip at about 20 megahertz. Here's about 40 megahertz. It's dipping down to 1.1. So we're seeing a, you know, a SWR of around 1.1, about 20 megahertz and about 40 megahertz. And there's something here, but who knows what it is. But what I do in the algorithm I've implemented, I try and scale this to get the maximum resolution. And because I do that, you may see things like this. You may see dots, which is normal. It just, the resolution, the vertical resolution is so high, right? But pay attention. You may see these huge dips and go, "Oh my God, that's huge!" But it's still 1.1. It's about 1.1. But all of a sudden, you may start seeing some junk, which may not be present here. So you just got to be aware of that. That's just junk, right? So we may see some more jaggedness because of that scaling. For crystal 3 dB sweeps, this is extremely important. Okay, the way I calculate the motional parameters is I take a look at what the maximum of the peak of the crystal is, and then from that I look at what the insertion loss is. I need the insertion loss. Then I roll that back to get to 3 dB to say, okay, from that point 3 dB down, what frequencies do I get? And I get my bandwidth. So the bandwidth, the center frequency, and your insertion loss, those are all important when calculating crystal motional parameters. So the reason this is important is if your crystal has any ripple in it, okay, when I get the peak, am I going to use this peak? Am I going to use this peak, or am I going to use this peak? And is this peak maybe the 3 dB points here, if you've got the ripple too big? So if you've got any kind of ripple with your crystal, this won't work. Okay, and same thing with your 3 dB sweeps. There is an option where it'll calculate your 3 dB points for a filter. For example, if your filter's got ripple, it may not work. Okay, and same thing goes if you got a flat top like this. How does it know where the center frequency is? I don't do any special curve fitting to say where the peak is. I'm just trying to wing it and figure it out the best I could. Because keep in mind, this is a bloody Arduino. This is not a PC. It's an Arduino. It's got limited horsepower, so, and it's got very limited floating point. So I have to work within that. Okay, so I call this the Peter perturbation. I have no idea why. I asked Peter, and Peter has no idea why. But basically, to measure crystal, you need to have a jig. And a crystal is somewhere around 12, ish ohms. The nominal impedance of a crystal is 12 ohms. So your SNA is feeding 50 ohms, 50 ohm signal, and it's got a 50 ohm detector here. So if we were to connect that to the crystal, it would load that crystal down and the Q would suffer because of that. And so because of that, we put a 50 ohm pad here to force 50 ohms, take it down. And we've got a 2-to-1 transformer. So to take 50 ohms to 12.5, because I think 2-to-1 the turns ratios the impedance squared, or something, turns squared is impedance, or something like that. And same thing, you got the same transformer here to try and force this to be 50 ohms. Now, if you go to my crystal how-to video, you'll see in here, I talk about the jig. Where is it? Somewhere in here. Yeah, I talk about the jigs. The quality is the video is terrible. So I talk about the jigs and so forth. And one of the things I suggest doing is, instead of using the calibration for a straight through cable, you run a calibration using this with this shorted. You short the crystal, you put a short jumper across here, and you sweep it. So all of a sudden now all measurements are relative to any losses across here, right? And in this video later on, in the video, I don't know why I clicked that again to get it started again. It's really stupid. But if you go later on in the video, I do talk about that somewhere over here. Yeah, I talk somewhere in here. Anyway, you could go look it up and see what it's saying. So, and the other thing too to pay attention, I think this might be why I called it the Peter perturbation, is that if you look at, I wrote this program here to analyze crystal filters. Okay, so if you look, this here's a crystal filter, and these are the crystals that Peter measured. These are all the motional parameters he measured. And if we do a sweep of this, and it's we assume it's terminated to 500 ohms, so you get ripple. You get the ripple in the passband here. The orange, this is actually doing a Gaussian curve fitting because it's a PC running this. But if we go and we optimize it, and it should be actually 310 ohms, the impedance, and we do a sweep, notice we get a much better behaved curve. We get less ripple in the passband here. So I think that's why I was referring to it as a Peter perturbation, because if you don't have this crystal terminated properly, you may get some ripple. I don't think so, because I think it'll just impact the Q. You'll get a wider bandwidth for the crystal, and that's it. So I'm just quickly showing the schematic. I'm not going to go through this, but here's the 8307. You could see it's on an isolated ground plane. There's a 0 ohm resistor connecting the two ground planes together, and everything that feeds into this section has a filter. This one has a LRC filter coming in, and this connection here has a RC filter. So we filter anything going into here to try and reduce the amount of noise that the 8307 would have. So that's it.